Greetings, this is Brennan, and welcome to Brennan's Biology. As a quick disclaimer before we start talking about the molecule of today's session being dopamine, I'm not a doctor. Don't take anything I'm saying as medical advice. I'm just an educator. Having said that, we're going to talk about dopamine now. This is the molecule right here. Sorry about my not too good handwriting. And this is phenylethylamine. It is released by the body, and it acts as a releasing agent to release dopamine, norepinephrine, and epinephrine. This is also the basis of the amphetamine molecules, and is a stimulant. It's naturally released by the body. So dopamine, there's 5 receptors: D1, D2, D3, D4, and D5. One thing I think is profoundly misunderstood about dopamine is that dopamine is the pleasure molecule. It's not the pleasure molecule. When dopamine levels is high, it makes activities seem worthwhile, and actually that has to do with the D1 and D5 receptors. D2, D3, and D4 are actually inhibitory. They lower activation and inhibit the central nervous system. They make you not, and when they're agonized or triggered, they lower activation in the brain and actually make you less motivated. So dopamine isn't necessarily the pleasure molecule. It isn't not the pleasure molecule. It does a lot of things in the brain. And this is just what we know about. There's still a lot of research being done. But let's get into it. So D1 receptor. The D1 receptor increases intracellular levels of cyclic AMP by activating adenylate cyclase. It is the most abundant dopamine receptor in the brain, and when activation is high, people are happy, and doing tasks feels worthwhile. It makes tasks seem worthwhile, like you want to initiate tasks. Agonists include phenylephrine, which is an antihypertensive drug, which is interesting. This receptor is not the target of many agonists and antagonists. Activation of this receptor pharmacologically is generally done with releasing agents such as amphetamines. So there aren't really many direct agonists and antagonists. Now we're going to move from D1, which is an excitatory receptor, to D2, which is an inhibitory receptor. It decreases levels of cyclic AMP by inhibiting adenylate cyclase. Adenylate cyclase. This receptor, when activated, it was neuroprotective against toxins such as MPP+. It is believed that this receptor, when activated, increases the vividness of memory and triggers specifically traumatic memories, makes them especially vivid. Hence why it is the target of first and second generation antipsychotic drugs. This receptor is, when antagonized, it decreases the severity and occurrence of psychotic symptoms. It is a target of things like thorazine and haloperidol. So those are 2 examples. Those inhibit, among other things, the D2 receptors. The D2 receptors. Now let's go to D3. D3, when decreases levels of cyclic AMP by inhibiting adenylate cyclase, like its D2 cousin. This receptor also is the target of antipsychotic drugs. This receptor is very common. It's very common in older parts of the brain, and is thought to be play a crucial role in emotions, emotional actions, and how emotions play out in the brain, and especially in areas like the amygdala in the lower brain areas that aren't new or evolved. It is believed this receptor plays a major role in emotions and cognitive function. Being when triggered, it generally increases memory. Now let's go to D4. D3 is also the target of antipsychotics, but D2 and D4 are the major targets. D4 decreases it decreases levels of cyclic AMP by inhibiting adenylate cyclase. This receptor is also the target of antipsychotics, an example of which is namonapride. This is a Japanese antipsychotic used to treat schizophrenia. This is because activation of this receptor is associated with many psychological disorders, including anorexia nervosa, schizophrenia, bipolar disorder, borderline disorder, and ADHD. So this receptor plays a big role. Well, I don't think it has been researched as much as it should be. It also hasn't been it hasn't been, well, pharmacologically, it really hasn't been studied a whole lot. And I think that's a big shame. And let's move to the D5 receptor. So like its cousin D1, the D5 receptor is excitatory, being it increases levels of cyclic AMP by activating adenylate cyclase. One thing to note about this receptor is it's pretty evenly spread throughout the entire nervous system, and it affects organs like your kidneys. So when it's triggered, it'll facilitate kidney function. So as opposed to D1 that's located throughout mostly in the brain, D5 is throughout the whole body. Ready? So, this receptor increases brain-derived neurotrophic factor, and it increases the phosphorylation of protein kinase B. What I find interesting about this is give me one sec. Is brain-derived neurotrophic factor. It increases neurogenesis in the brain, so the growth of new neurons. It also increases the survival rate of these new neurons and the formation of new neural connection, and which I find very interesting. So it increases the phosphorylation of protein kinase B. It is very similar to the D1 receptor, but it is not however, it is not the target of antipsychotic drugs, and it is found all over the nervous system. It's also known to play a major role in memory formation, and memory formation and your ability to recall things. So it has a major memory thing there. It's very interesting. Again, it's not very pharmacologically studied, and when you want to activate this receptor, generally what's done and would be to use not a direct acting agonist, but use a releasing agent like amphetamines. The amphetamines which go into the cell, go into the vesicles, and cause the body to squirt out a lot more dopamine than it otherwise would do. So I think that really covers everything I wanted to say in this video. Thank you very much for listening. Please comment down below. I would love to hear what types of biological things you want to hear me talk about. Thank you very much for listening. Please comment below and subscribe. Bye.